Good morning, team. Are you guys ready? This is where we put it all together. This whole quantum mechanics development we've been doing, everything we've been talking about, leads us to this. The ultimate question. Here's an atom or some species, maybe an ion, whatever it is. It's got this pile of electrons. It's got this many electrons. Where do they go? Right? Where are these electrons? Because now we've carved up this space around the nucleus. I guess you can think of it that way. And we got these electron seats, just like if you're in an auditorium, you got seats where people can go. Those seats are there. We just got to put bodies in them, right on? So let's look at how we distribute these electrons within all of these available orbitals. Obviously, we have more orbitals available than we have electrons because there's only so many elements, right? So we got way more space than we have electrons. So we'll never run out of seats for electrons, trust me. So that's what an electron configuration is. Just how we distribute all of the known electrons for any species amongst all of its different orbitals. Yay! Obviously, there's some rules for that we need to follow. And of course, just like most of chemistry, there's exceptions to those rules. I'll keep it simple. It is general chemistry. We're not doing physical chemistry or inorganic chemistry or something like that, where we tend to focus more on some of the exceptions. So I'm going to just give you the basic guidelines and then talk about a few exceptions here and there, but none of the weird ones down towards the bottom of the periodic table. All right, you can read those on your own if you want, or if you become a chemistry major. So a little review. Remember, there's 4 quantum numbers. 3 of them, the principal quantum number, angular momentum quantum number, and the magnetic quantum number. Those describe the specific electron seat, the orbital. Right? Gives you the size or energy, the shape, and the orientation. And then electrons are designated by the electron spin quantum number. So either it's spin up or spin down. And we're going to draw an arrow pointing up or an arrow pointing down. All right? So when we do electron configurations, we're not concerned about the actual quantum numbers. We're not going to write ms equals positive 1/2 or something like that. But when we do the designations, we do have to designate which orbital it is, which we talked about earlier, like a 4s or a 3d or a 5f or something. So we give the principal quantum number, we give the angular momentum quantum number, but as a letter, s, p, d, or f. But depending on the types of electron configurations, very rarely do we designate the specific orbital like it's a 4dz squared or something. We could, but typically we just look for the sublevel it's in. But 4 different ways we're going to write these electron configurations, so we got to go through the rules, these 3 main rules. Let's talk about those first, then we'll look at the different types of electron configurations. Some of them are shortcuts, some of them give you more information. It all depends on what you're after. Some terminology, and then we'll have at it, gang. Let's see if we can get this done in one video. Maybe, maybe not. All right, not going to do these rules in any specific order. I guess they don't have to be in a specific order, but let's start with the Pauli Exclusion Principle. Really, really important, gang. This has huge ramifications. So in 1926-ish, Wolfgang Pauli, right, was looking at spectroscopy stuff, looking at electron spins, where electrons were, what orbitals, yada, 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 and then found from his data and then proposed that no 2 electrons could have exactly the same 4 quantum numbers, n, l, m sub l, and m sub s. Right? That would be akin to going to a concert or something, and we describe a seat, right? If it's a multi-layered musical theater, say you're going to see Hamilton or something, and you need 3, right? The level, the row, and the seat. Those 3 quantum numbers tell you what seat it's in. But once you're in that seat, no one else can go in that seat. Right? You would occupy, you'd have to be a ghost, to occupy the same spot, unless somebody sat in your lap, but they wouldn't allow that at the theater, as much as I tried saying, can I just buy 1 ticket and just sit in the same seat with my wife? Yeah, save money, like in an airplane or something, but no, they don't allow that. Oh, darn. All right, I would save so much money. Everything would be half off. Well, the rules are a little different in the quantum world, because when we sit in the seat, we sit on our tushy, right? We don't sit on our head. We don't do weird things like that. But in the quantum world, you can have 1 electron seat, that orbital, designated by n, l, and m sub l. So 2 electrons could share those same 3 quantum numbers. But remember, there's 2 spins, spin up and spin down. So as long as the electrons have opposite spins opposite m sub s, one's a positive 1/2, one's a negative 1/2, they could both go in the same orbital. So in the quantum world, yes, you can have two electrons sitting in the same seat. As long as they are opposite spins. Otherwise, they'd have the same spin encompassing the same space. That just can't happen. So this is a critical, and there's some ramifications for this that I want you to think about before I go on the next board. What does that mean if I could have two electrons with opposite spins in the same orbital? Oh, let's ponder that. Here are the ramifications of the Pauli Exclusion Principle that will help us when we do electron configuration. So good things to know. So this means we can have two electrons in an orbital, right? As long as they have opposite spins, right? And typically we always start with spin up, right? So if there's just one electron in an orbital, we always put it spin up. Doesn't have to be, but that's just tradition, right? Spin up. And if you have to put a second one in there, blip, it goes spin down. So you have an arrow pointing up and an arrow pointing down. Also, that creates a maximum number of electrons that can exist in a particular subshell, S, P, D, and F. Now remember, the number of allowable magnetic quantum number values, the M sub L, is the number of orbitals, right? So we had S is 1, right? S is 1 orbital, P was 3 orbitals, Px, Py, Pz. D was 5 orbitals, dxy, dxz, dyz, dz squared, then dx squared minus y squared. Oh, no, those! And F had 7 orbitals. Don't need to know those designations, right? But 4 had 8 lobes and 3 of them were p orbitals with 2 hula hoops around them. Well, just take the number of orbitals times 2. That would give you the maximum. You could, of course, have less. It could be empty, but maximum number is 2 times the number of orbitals. So an S sublevel, 1s, 2s, 3s, 4s, can have 1 orbital times 2 is 2 electrons maximum in it. There's only 1 seat. But in a P sublevel, Px, Py, Pz, I could put 2 in each. So 2 times 3 is 6. So I can have a total of 6 electrons. We're going to associate this with the structure of the periodic table later, right? Yay! Which I think Bohr started doing, actually. Somebody started putting this together. I can't remember who. D has 5 orbitals we talked about. 5 times 2 would be 10 electrons max. You'll see that on the periodic table as well. Well, I'll give you a little glimpse here. See here, right? You see these two groups across, 1, 2. This is what we call the S section, right? The S group. Now notice how many are across here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, isn't that nice? So I wonder what these transition metals have with 10 elements across. Oh, D. So these are known as the D subgroup. S subgroup, the alkali metals and alkaline earth metals. The transition metals are the D. Well, how many are across here? And these representative elements. 1, 2, 3, 4, 5, 6. 6! Oh my gosh! So this is your P block. So you got a P block of 6 across, a D block with 10 across, an S block. And gosh, let's think about what these are. If you have 7 orbitals in the F subshell, times 2 is 14. How many do you think go across the lanthanides and actinides? 14. It's like magic. Thank you, Pauli Exclusion Principle. Of course, named it after him. So let's look at the next one. All right, next rule is Humps Rule. Looks like Hund's Rule, but I think it's Humps Rule. Sorry, I didn't bother to look up the date for this one, so I haven't opened the door to every rabbit hole possible. We just don't have enough time. Plus, I have 4 kids at home. So limited amounts of reading I can do. Sooner or later, I'll look into that. I love when I have time digging into the history. I think it's just fascinating how these people thought and what they put together. It's astounding. So what Hund's Rule says that is, okay, while we're filling electrons into orbitals, what if you run into a set of orbitals that are exactly the same energy? That's a degenerate set. And that's what we get from the subshells, S, P, D, and F. Now, remember, the subshells themselves, because of electron screening and orbital penetration, S is lower energy than P, than D, than F. So those have a distinct order. That'll be the next rule. We'll go in the order go to the lowest energy ones first. But like if I'm in the 3D subshell, there's 5 orbitals. The dxy, the 3dxy, 3dyz, 3dxz, 3dz squared, and 3dx squared minus y squared. They're all the same, exactly the same energy at this point. That will change a little bit in one of the later chapters next semester. So if you have an electron, it doesn't care which one it goes into. That's why a lot of times in electron configurations, we don't need to designate which specific orbital it goes into, right? So usually we just think in terms of subshells. Oh, it goes into the 3D subshell. We don't care if it's the dxy or the dz squared because it's the same energy. But once you put one in there, where does the next one go? Right? It's like getting on I call this the bus rule, right? You get on a bus, and let's say you got a bus, you go in and all the seats can hold 2 people, right? So you can either go to an empty seat. You can't sit in a seat that has 2 people, it's full, or there's seats with only 1 person. And typically when people fill in, they only sit together if they know each other. You know what I mean? So say you go in and you look on the bus and all the seats are filled except for 2. One of them's empty and the other has a stranger in there that's looking at you real weird. Yeah, come sit here. Oh, sit here. You're like, don't think so. You're going to sit in the empty one, right? You want your own space. Okay, really what it's doing is it's trying to maximize the attraction to the nucleus. So what they have found is if the electrons go into separate orbitals with the same spins, we'll do all spin up in my class, we start with all spin up, in separate orbitals, got to keep them separated, right? That maximizes the nucleus electron attractions there. Just think, another way to think about it is they're both negative and they want to stay apart from each other if they possibly can. So they will only pair up once all the seats, once all of the orbitals within that degenerate set have 1 electron in it, then they're forced to start pairing up. All right? So that's Humps Rule, and that will end up maximizing the number of unpaired electrons. And remember what happens when you have an unpaired electron, right? If they're paired up, the magnetic spins cancel. If it's unpaired, that creates a magnetic field which interacts with an external magnetic field we'll talk about later. Woo, let's look at the last rule. Before we go to the next rule, let's do a pictorial view of Hund's rule so you can see what's going to happen. Now, you will run into these. A lot of times there's one type of electron configuration we're going to run into, my personal favorite, called an orbital box diagram, where you draw each orbital as a box. That's why it's called an orbital box diagram. You don't need to designate which is which, but we could if we wanted to. So imagine there's 3 of them, so this would be a P subshell, right? So let's say this is 4P. So we just kind of label that subshell down below it. And let's say we have 3 electrons that need to go into a 4P subshell. So let's use arrows to designate, up or down. Spin up, arrow up, spin down, arrow down. Let's do it incorrectly. Let's say we have 3 electrons. Well, it doesn't matter which one you put. The first one, pick your poison, doesn't matter. But typically I'll always put in the first one, but you could put it here, you could put it here or here. It doesn't matter. But typically we'll put the first electron as an arrow pointing up, representing an MS positive 1/2 spin up. Okay? The second electron, now we have an option. It can either go into an empty seat or it can pair up. The incorrect way would be to pair it up, which would be a spin down. Otherwise, if they're both spin up, you're disobeying the Pauli Exclusion Principle. Now that one's full, so the next one could go here or here. That's the incorrect way of doing it because you've paired up the electrons when that electron would rather be in the empty orbital, right? So the correct way to do it, if I have 3 electrons, I would go 1 in the first one. Doesn't matter which one you put it in. The second one would go in one of these other 2. We typically go in order. That's Hund's rule right there. They want to stay in separate orbitals as much as possible. The third one would go there. Now, if we had a 4th one, it would be forced to pair up in one of those. And again, you're welcome to designate. You could go 4px, 4py, 4pz, but it doesn't matter because they are degenerate. Now we can do the third rule. All right, last but not least, the Aufbau Process, all right? So if you know your German, you would know Aufbau. I don't know German. One of my best friends is fluent in like 5 languages, German, flawless speech in German. So, hi, Carl. So Aufbau is German for to build up, right? Build up, and rise up. Sorry, my kids keep singing Hamilton all the time. So the song's just da-da-da-da. This is fun. It's very catchy. Anyway, so what this essentially means is as we're moving along the periodic table, right, going from hydrogen to helium to lithium, beryllium, and boron, carbon, nitrogen, oxygen, fluorine, we're increasing in atomic number by 1 proton at a time, right? But if it's a neutral atom, as you add in a proton moving along the periodic table, you're also adding an electron to keep the neutrality of it, right? So we're building up along the periodic table. Well, if we are adding an electron each time, where does that electron go? What orbital? It will always go into the lowest energy orbital available, right? So if the lowest energy ones are full, it will go in the next highest energy one, right? It's just like I said, when I go to an open seating concert, you know, I'm rushing the stage, baby. I want to get as close to the nucleus, i.e. the stage, as I possibly can, right? My first concert was a Kiss Winger Slaughter concert. Me and my buddy, Jerry, man, we got in there and we packed, slid our way through people to get as close as we could to that stage, and the speakers, your heart was, I went to a thing out here in Riverside County that the Foo Fighters put on. I forget what it was called. And I was there the whole day, and I brought my exam. That's how nerdy I am. I had to grade all these exams. So I just went early, and I'm watching all the starting bands, right? There's hardly anybody there. And I just sat down and grading papers, and I'm way up close. There's hardly anybody there. And the speakers, my whole body is just, my eardrums are screaming, ah, right? And man, when the Foo Fighters came, I was way up close. I'm like, oh, Dave Grohl, right? Oh, so awesome. That's how you work, baby, at a Foo Fighter concert. I wish I didn't have to grade papers, but you do what you got to do, right? Anyway, you got to have fun in life. Work hard, play hard, baby. So we need to know one thing in order to do this. What's the order of energy from lowest to highest for all of the sublevels? Remember, the orbitals within a sublevel are degenerate, so we don't care about individual orbitals. We care about the sublevels. So what is the order of the energies of the sublevels? We know S is below P, which is below D, which is below F, because of the degeneracy breakdown from electron screening and orbital penetration. But let me show you a little trick. There's two ways you can do it. You can use the periodic table, all right, if you know how it's organized, or you can use this little trick. I think that helps a lot of students. Some of you just memorize it. I've always had trouble memorizing things. It goes in and then leaks out pretty fast. I can puke it out on a test and then I forget it all. So I try to work with patterns or, you know, algebraic substitutions and derivations, because then you know how to do it. You don't have to memorize it. But let me show you a cute little trick here. Here we go, gang. You ready? You've probably seen this before. If you haven't memorized it or used the periodic table, you can just write this cute little trick. It's easy to do. Just start with the first column with your S's. Just go 1S down to, I mean, you can go down to 27S if you want, but you really don't have to go past 7 because we don't have that many rows on the periodic table, right? Think of that as n equals 1, n equals 2. And then the second column, we start with the P's. Now remember, the P sublevel doesn't come until the second energy level. There's no such thing as a 1P. So you go 2P, 3P, 4P, 5P, 6P, 7P. You can go as far as you want. Now remember, the D's don't come in till the third, till n equals 3. So now we pop in the 3D. So notice across a row are all 1s, 2s, 3s, 4s, 5s, 6s, 7s. Going down columns are S, P's, D's, F's. You could go to G's and H's and all that kind of stuff too. So 3D, 4D, 5D, 6D, 7, even though we don't have elements that get into the 7D, you could. And then the F doesn't show up till n equals 4. So we got the 4F, 5F, 6F, 7F, even though I don't know anything that's in the 6F and 7F. So it's pretty simple to draw. Now, if you want to know the order of increasing energies, let's draw a little energy scale, which you don't need to draw, but watch how this works. You're going to start in the upper right and come down diagonally to the left. Right? We all know 1S is the first one to fill. That's the front. There's only one seat in the front row of the concert, baby, but 2 people can sit in it as long as they're upside down. So we're going to come through and go boom. So the first one we hit is 1S, which has 1 seat, correct? So we can pop 2 electrons. So that first principal energy level can only hold 2 electrons. Now, there's nobody here. So we go back up to the top and come down, and we hit the 2S. So that will be the next one. Let's do that in a slightly different color. Now, I'm not going to accurately, really, they start pretty highly spaced, and then they crunch up closer and closer together. As you get up higher, they get closer, 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 closer together, because that 1 over n squared energy dependency. That creates issues when we're doing electron configurations. So essentially, the farther down the periodic table, it's pretty standard here, but you start getting down here, some weird things happen. They're actually kind of cool exceptions, but it's studied more in like junior level inorganic chemistry or something like that, right? All right, there's nothing left here, so let's move back up, which would make sense. You'd think the 2s would fill first. So we come here, we hit the 2p, right? So the 2p is next, and that has 3 orbitals that are degenerate, correct? And then after 2p, we hit the 3s. So let's pop the 3s in there. Right, so we're going to put 2 electrons there before it jumps up, right? Because that's lower energy. So the electrons will pair up before it goes to the 2s. The 2s will fill up before it goes to the 2p, and then you put 1 here, 1 here, 1 here, according to Hund's rule, and then fill that up before it jumps up to the 3s. Right? See the way that goes up? Building it up. All right, nowhere to go, so let's go back here, and we hit the 3p. So that has 3 orbitals. So the 3p would be next, and then the 4s. So everything seems good so far. 1 fills before 2, 2 fills before 3. Everything seems hunky-dory, but wait! Remember, electron shielding and orbital penetration, s orbitals penetrate more, the electron density is closer to the nucleus, creates problems here. Boom! 3d is next. What? 1, 2, 3, 4, 5. The 4s fills before the 3d. Darn that little s orbital. That 4s orbital's got more orbital penetration and creates it's a little bit less energy, so it tends to fill before the 3d. They're actually pretty close in energy, but 4s definitely fills. So once the 3d is filled, then we go to the 4p, which has 3 orbitals, right? And once the 4p is filled, we go to the 5s. I think what we'll do is we'll just make this video rules for electron configurations. So, because if you know the rules, electron configurations are easy peasy as long as you're aware of a few exceptions. So the next video, we'll look at the types of electron configurations, special notation, and we'll do a whole bunch of examples. That way we're not rushing it on this one. And you can take a potty break or a food break. Go get that peanut butter and pickle sandwich, baby. All right, no more left. What's next? Boom, 4D. You see how the 5s fills before the 4d? Orbital penetration and electron shielding. It's screening out. The 5s is screening out the 4d, and its orbital density kind of has a little peekaboo towards the nucleus. This way, it takes account all of that. So the 4d fills up, then the 5p, and then the 6s. Everybody doing good so far? Now look what happens. We're done there. We come up. Finally, we hit the Fs. 4F. With its infamous 7 orbitals in there. Finally, that fills up. And then the 5D. I'm running out of space, gang. These are so close in energy, we're going to see some exceptions where they're jumping around back and forth. After 5D, we get 6P. Whoops. And then we get 7S. I think I'll end it there because I really can't go any further. And then after 7S, we go 5F, 6D, 7P, 6F. Right? See how that goes? Moving along. 7P. That would technically go to the 8S, but we don't have any elements that far out. That's probably good enough right there. We're going to be rocking and rolling. So hopefully you can do that. And I'll draw a picture on the periodic table that represents that real quick. All right, if you want to follow the way the periodic table's arranged, and again, Niels Bohr was kind of looking at this, this is the second way you can figure out the energy levels if you understand it. There's a little trick to it. It's pretty straightforward. So obviously we got row 1, n equals 1, 2, 3, 4, 5, 6, 7. That kind of represents the energy levels. So as we start across, we see these first two. This is called the S block in purple here, right? Remember, we have one s orbital. We can do 2 electrons. So 1s1. Now helium we put over in the noble gases, even though it's still technically 1s. It would fit better there. Hydrogen's not really an alkali metal either. So hydrogen, some people actually put hydrogen over here. Some people put hydrogen up here. It all depends. So hydrogen's kind of a wacko one. But so that top is just the 1s, and then the 2s, 3s, 4s, 5s, 6s, 7s, 2 electrons, right? Represents it, with hydrogen here and helium there. So remember, helium's not considered p block, it's considered s block. So it's kind of looks like it's in the wrong spot. But it needs to go with the noble gases. And that's it. That's all it's in the first energy level. Now the second energy level, you get S and P. So we got the 2s, and then we jump across and go to the 2p. Now notice all of these in green. We've got 2p, 3p, 4p, 5p, 6p, 7p. That's your p block, right? So your representative or type A metals. So your representative metals we talked about in the beginning would be your S block and P block, right? Some are metals, some are non-metals. And then in the center here, your transition metals, which is your D block, right? 5 orbitals, total of 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. P block, 3 electrons, 3 orbitals, 6 electrons. 1, 2, 3, 4, 5, 6. So you can just see what blocks go across. It's pretty easy to identify. So purple's the S block, green's the P block, blue is the D block. You can see across here. But notice how they're shifted down. The 3D sublevel falls in the 4th energy level here. So as long as you understand that the Ds are shifted down by 1, you can easily follow across. So if I'm doing electron configurations, trying to figure out this Aufbau process, I just go 1s1, 2s1, 1s1, 1s2, and electron goes here, and then I jump into the 2p, fill that up, then I jump to the 3s, fill that up, jump to the 3p, fill that up, jump to the 4s, fill that up, then I jump to the 3d. So the 4s fills before the 3d, kind of what we did when we did those downward trajectory arrows on the last board. So there's all your D block. And then remember with lanthanum, there's a little star, and it comes down to the lanthanides. And then actinium comes down to the actinides. So this is your 4F and 5F, which is your F block. We do that in red. Those actually technically should be inserted right in there. It just makes the periodic table too long. So it gets a little tricky. Some people actually pull lanthanum and actinium down here to give you a feel, because the electron configurations are a little weird right there because you're getting further down. But in general, we would go 6S, and then 4F, and then 5D. And then 7S, and then 5F, and then 6D. You see how that tracks? So I don't care which way you do it. 3 ways. Memorize the dang thing, follow the periodic table, or do that thing where you do the S's, P's, D's, and F's, and you do the downward trajectory arrow. So that's the rules. We'll do another video. Let's look at the 4 different types. One of them's kind of silly. So really 3 different types of electron configurations, and do a whole bunch of examples.